The only energy had is a change of kinetic energy. What happened? Where did the kinetic energy go? Well, there's no friction on this surface, we were told. So the kinetic energy went where? It went into potential. So let's make, so all the kinetic went where? When it's fully compressed, all the kinetic went to potential, which is 1/2 kx squared. So let's make an equation out of this. I think the question, well, what was the maximum compression? That's x. So 1/2 mv squared, all kinetic. Where did it go? It went to all potential, kx squared. Let's cross out the halves. Divide both sides by k. So mv squared divided by k is x squared. We're running out of room over here. Let's go x squared. We divided both sides by k. M v squared divided by k. Take the square root and get rid of that get rid of that squared. And so you have an m, you have a v, which is right over here, there, and you have a k. So you just square that v right over here. Multiply it by, well, actually the m would be 3m, wouldn't it? Or actually 4m, excuse me, 4m. So you'd have, you just, I'm running out of room, you do substitution. You have the mass is 4m. The velocity of v is v0 divided by 4. That's got to be squared. Looks like divided by k. You can clean that up. I mean, that's just math after that. This 4 gets squared. It becomes 16. You cancel out the 4 in the top. It becomes v squared over 4 divided by k radical. Okay? Elizabeth, did that go too fast? Or
No, that was good. Thank you. Is
Yeah,
there
yeah.
something like that on the midterm?
Well, there's definitely a collision question, but nothing this involved. Is there a spring? I can't recall. But how do you know? People always ask me, especially towards the end, how do you know what to do with physics? Collisions, what do you do? Total momentum before equals total momentum after. Energy changes like a velocity change. Well, that's a height change. A spring compressing, that's all energy. That's an energy problem, that the energy before equals the energy after. As long as there's no friction, the energy is conserved. I think somebody raised their hand. Who was that?
That was me.
Okay, Gabriella. What do we do,
So
Gabriella?
K is the spring constant,
Yep,
right?
yep.
And if that is on the test, I know you said you don't remember, but if that does end up being on the test, will it give us that?
Oh, well. No, what you were asking is for the compression. That was she wanted me to reconstruct the question from the test, and remember that answer was all in terms of the variables given, in terms of k. So we don't have to know k, m, or
Okay.
v because the question was what is the answer in terms of all those variables.
Okay.
So yeah, of course, if they wanted an answer, they have to give you what all that stuff is. Okay.
Thank you.
Anybody else look at stuff and say, "Gee, I really don't get it," even after the video, even after the looking at the answer key? Does anybody just
Can
call
you
out?
guys do one finding tension?
You want to do a tension one?
Yeah.
Sure, that's a good one. Okay, let me clean this up. All right,
Actually, can you do an energy one?
an energy one. So a tension one is how about would you like me to talk about this one, or is it a pulley tension? This is a tension one. This is a tug of war. Do you remember this one? Or is it tension with like a pulley? Which tension?
No, something like this.
Like this? Okay. You got two physicists playing a tug of war. This rope is light. That just means you don't have to account for it. You've got a hanging 70-kilogram mass. I'm definitely making a picture. I hope you would. It's an equilibrium. That's key. What does that mean for us? F net equals 0. Sum of the forces in the x and the y direction equals 0. That's why I underlined this. You've got the two rope angles, and I'm underlining this as well. What are the tensions of these unknown ropes? You have two unknowns, and from math, I better have two equations, or I'm definitely not going to solve this. I actually do have two equations because the sum of the forces in the x direction equals 0. So the left force equals the right. Well, take a look at T1. What's the left force? It's the horizontal component. So it's a little sloppy, T1 cosine theta. equals the right, T1, T2 cosine, because that's the adjacent side. So the left equals the right. Notice I, do the trig, solve for T2. Somebody asked me, could I solve for T1? Absolutely. In math class, it doesn't really matter, does it? What you solve for one of the variables, I solve for T1, but you can solve for T2. How do you do that? Divide by the coefficient in front of T2, like divide both sides by 0.86. I actually know what I did. I multiplied both sides by 2, and I got T2 is this number. And then sum of the forces in a y direction equals 0. That there are two up forces, the vertical components of both the tensions, and they equal the one down force, which is the weight of that box. And so now I just bring it over here and I substitute. Now I'm running out of room, but for T2, I put 1.732 T1. And now the only thing I have in my equation is T2. T2, okay? Is that anything you want me to go over again? Because maybe I went too fast.
What does it mean that the rope is extremely light in comparison with
You know what that means is when they're telling you, you don't even have to account for the rope's weight in your equations. If they say a pulley is massless, well, then the physics is gone. It's not contributing anything to acceleration. It's kind of really saying we're going to make this problem all about the rope tension and not the mass of the rope. It's not. In other words, it's not adding another downforce. If it was like a cable, that actually had a weight, well, now you have the, which is very rare. You have three downforces. You have the 700 newtons. You've got the weight of the right chain and left chain, and that's two downforces, and so it makes it a lot more complicated. So that's typically what they do is eliminate the weight of the rope, so it's not part of the equation anymore.
Yeah, but aren't all of our ropes weightless as of right now?
Yeah. At this point, yeah. And all our pulleys are massless at this point in the year. Does anybody want me to do a pulley? I want to talk about this pulley, and anybody want me to just turn on your audio and say yeah or no?
Can you do this one?
Yeah.
Okay, so we have a classic pulley. This pulley is massless because we're not ready for anything else. It'll come in the fourth quarter. And you've got two boxes, and they want me to actually answer in terms of M. So I go, okay, we've got a system. I'm going to use a whole system method because let's see what the question is. Free body diagram. Okay, let's look at this box 3M. I think a lot of people notice that the string going over the pulley is a single tension. We say one rope, one tension. Now, in the fourth quarter, that's not true because our pulleys will no longer be massless. But right now, if our pulleys are massless, then it's one rope, one pulley. So we have one rope here, that's T1. And what are the forces on it? Well, there's the weight. Don't people forget the weight because it's an invisible force, but 3 mg is a down force. T2, the tension of this below, there's one string below and there's one string above, and we'll call it T1. And so that's the free body diagram. Now, here's a thing I want you should know on part 2. I believe I say I need to see relative sizes. What does that mean? Well, if two forces are equal in your picture, you got to make them equal size. If you believe one is bigger, well, then you have to do that. Now, when they don't say that, then it's just it's a sketch. But I do at some point say show the relative sizes. Relative means how one relates to the other. Looking at this picture, this system is going counterclockwise. So the sum of those two down forces would be greater than the up force. Now, I did not ask for the relative sizes, and this problem doesn't. So it's just a sketch, a rough sketch. So relative sizes means if one force in your picture is equal to another, make it the same size. Even if it's equal but opposite. If it's bigger, make it bigger. All right. So what is the acceleration of 4m? Don't fall into the trap of, I guess you could isolating on 4m. No. Let the whole system moves with the same acceleration. So what did I do instead? I used the forces on the outside of the system. What do I mean? Well, there's a force going to the left, 5 mg. Those two boxes have a weight, 5 mgs. There's a force that's your positive. Notice I put those counterclockwise. I saw the two boxes on the left were bigger. So I said this system's going to go counterclockwise. Why? Because there's a weight going counterclockwise that's bigger than the clockwise weight, 5 mg. So therefore, this 4 mg is my negative weight, right? You establish your positive, and as long as people typically call the direction of the. It's smart to call the direction of the way the system's moving is positive, or I think you'll get yourself confused if you don't. Divided by what is being accelerated by those two competing masses? Well, the whole system, 3 plus 2, 5 plus 4 is 9. And so when the top becomes mg, the m's cancel out, and g divided by 9. All good on B? There's something very similar to that. I think the one on the test is easier than that question that I have on the test, I believe is easier. All good? Can I go to C? C says, what is the tension supporting 4M? Well, now I'm isolating. Tension we're calling supporting 4M is T1. So I isolate. What does that mean? In my mind, I circle, and I have tunnel vision, and all I say is, what are all the forces acting on 4M? And I've got tunnel vision. I don't see, nothing else exists but all the forces on 4M. And so I say, well, the system is going counterclockwise. The T is in the counterclockwise direction. It's positive. 4mg is clockwise. It's negative. And what are those two forces accelerating? They're accelerating the 4m, and that's times a. And so that's Newton's second law, of course. And then what I do is I send the 4mg to the right by adding 4mg to both sides. And let's get rid of that a because we can. It becomes g over 9. And common denominator is 9. 36 over 9 is 4. So 36 plus 4 is 40 mg divided by 9. All good? Isolating. Can I go to D? Okay, I'm going to go to D now. Isolating on D. What is the tension on the 2m? So once again, I have tunnel vision. What are all the forces acting on 2m? My system's I'm going to call the counterclockwise forces 2mg, positive, and the clockwise forces T2, negative, and that equals what? Accelerates the 2m. F equals ma. Now, let me not do what I look at that. I'm not getting my full credit, so I'm going to get the full credit here. Get my F equals my physics points. I left that out. So I send the T2 on the right by adding T2 to both sides. I subtract 2 ma, and then so T2 is 2mg minus 2 ma. Where there's an a, I replace it with g over 9 because I got that from before. My system is accelerating with g over 9. 9 is my denominator. Gotta get a common denominator. 18 over 9 is 2. 18 minus 2 is 16 mg divided by 9, and there you go. Huh. Okay.
Mr.
Is that all?
Mitchell,
Go ahead.
is the 4M tension, can you call it T1 or is it just T?
Where's the 4m tension? Oh, I called it T1. You could, you
No,
call
for
it
like
anything. You really
the
can call it anything you
equation.
want, but you could even call it T. But the tension between 3m and 2m, it's a different tension, so you got to give it a different name on it. You can call it whatever you want to call it, but you can't call it T. If you call what I call T1, could you call T? Sure.
Okay, because I mean like the T equals 40
Oh,
mg.
you know what I'm saying? You know what? You're right. When I did that, hold on, let me. I think I see what you. I call it T. My bad. So we'll call it. Sorry about that. Good catch. Let's call it T1. Sorry about that. Yep, you're right. I didn't call it T1. So thanks for that catch. All right, good catch. Anybody want to talk about? So I think we've really covered that enough, and I want to cover different topics and not.
Can you go over number 8 on the like the midterm practice 1, the test wizard?
Sure. Okay, midterm practice. Is this the? Yep, good. Oops. Hold on, let me just undo those two straight things I just did. Okay. I'm sorry, what number again?
8.
Sure. 8 looks a little funny, huh? 8, rate. Oh, here's another pulley one. Well,
Hold on, wait. That wasn't my 8, sorry.
oh no, here's the 8. Here's the right. This one. Oh wait,
Yeah.
you have a different order.
I was talking about yeah,
Read it.
it says a block of weight W is pushed along a horizontal surface at constant speed V by forces F that act on angle theta.
I think I got it.
What is the magnitude?
Yeah, I got it right here, right? This is my 8, isn't it? This one right here?
Oh yeah, sorry.
Yeah. Okay, so great. I love this one for you guys. Good. I like this one. So a block W, weight W, that's a force. Weight means force.
No, I don't.
Okay, so you want to find
Ah.
normal force, right? So the normal force, the sum of the forces in the y direction. Oh, here it is right here. You see it over here? Sum of the force in the y direction equals, let me see. Yeah, what is the magnitude of the normal force? So the normal force is the floor's force up on the block, right? So the sum of the forces in the y direction equals 0. There's one up force, the normal, right? Normal. There are two down forces. Take a look at the applied force has a down component. We'll call it Fy. So the weight is down, the F sine theta is down, but the normal is up. So the up equals the down. What is the normal? Well, the weight is already given. That's 100. We were given that, weren't we? Yeah, 100. That's W. Now, all I have to do is 40 sine 30. You know what I should have done? I always tell you to put the information right in the picture, which I did not do, which I should have. So 40 sine of 30 turns out to be 20 newtons. So 100 plus 20 is D. Did you get that? Did you get that for the normal? Do you understand?
Yeah, thank you.
You want me to do it? Tell me.
Can you go over it one more time?
Yeah, no problem. I know the normal force, is the ground's force up on the box, right? That's the normal. And normally you might say, well, it's a flat surface. Doesn't the normal equal the weight force? Nope, because of this, right? Because this applied force is causing the box to press even harder on the ground. So therefore the ground will press harder on so the box will press harder on the ground and the ground will press harder on the box. It's called the third law. And I know that you get that there's some of the vertical forces, they equal 0. And so what does that mean? That means the ups equal the downs. What's the up? There's only one up. That's the normal. That's the ground's force in the box. But there are two downs so the weight is acting on the ground, but also F sine theta. Take a look at the picture. It's got a downward component. So there are two downs, mg, F sine theta, and there's a single up, which happens to be the normal force. That's good. That's exactly what I want. I'd see that the normal force is mg, which is given as 100, because they gave it to us right there, 100. And the F sine theta, that's 40 times sine of 30. They gave me the 30 as well. 40 sine of 30, when you punch it through, is 20. So mg is 100. And the F sine theta is 20. And there you go.
Thank you.
You're welcome. Eddie, just turn on your mic and call out a question of.
Why do you use sine instead of cosine for that one?
Oh, because take a look. The vertical component of this force is opposite the angle. You see that?
Okay, but then for like other normal force problems, you would use cosine normally, right?
Well, no. I mean, it would depend, but most of the time you use for normal force, you use the sine. Now, what angle are they giving you? There are particular problems, like everything else in physics. Sometimes you get a little bit of a weird problem where you actually, oftentimes it is the sine because the sine is the opposite of the applied force. Can you see that in the picture? How it acts downward. It's the part of the applied force that acts down, causes the box to press even harder on the ground. Any other question on any of these sheets?
For the tip sheet, is the level of difficulty kind of similar to the midterm?
The tip sheet. For which sheet we're talking about?
The midterm tip sheet that you gave to us that we filled in ourselves as a class.
Oh,
Is that level of difficulty similar
well,
to the midterm?
let me look at it. Let me see if I can pull it up. I think I actually have it somewhere here. I think I even have the tip sheet somewhere. Wait a second. No, I don't. I don't know. Is it similar? Is it the same? It's hard to judge.
Is it similar to these, like the midterm reviews that you gave us on Test Wizard?
I think it's similar. I would say it's similar in difficult. There are points that are a little difficult, more difficult than this. Let's see if I think it's similar to the midterm 1 and 2. And then let me see if I can pull up this tip sheet. Hold on. It's a tip sheet. I thought I had it. Let's see. Where's that tip sheet? I might have to just go to. Do you want me to pull up the tip sheet, or does anybody have any specific questions? It's hard. It's a
Is there
hard
a roller
question.
coaster question on the midterm?
You have a question on what? Which
Is
one?
there a roller coaster question?
I don't think I put a roller coaster cord. No, I don't think. I have no memory of putting a roller. Pretty sure there's not. Don't hold me to any of this. This is just. I don't believe there are any roller coaster questions. Go ahead. What? Just ask it.
For motion, will we, I know that we know that the Vy is 0 for a projectile, but
Well, said no. For a projectile, for an object, be careful. For an object projected horizontally, Viy equals 0. But after that, Vy for an object projected horizontally, here's something you're going to be tested on. An object is projected horizontally, Viy equals 0. That's on your tip sheet. And the Vy increases, but the Vx does not. Gravity is a vertical force. It only changes vertical motion. So go ahead, now ask your question.
yeah, will we ever have to find the Vy, because it increases? Because I know that it's V sine theta technically. Will we ever have to
Well,
find it?
now when do you use V sine theta? That's when an object is projected horizontally. So you could use
Yeah.
V sine theta. But if an object is rolls off a table, which there are a couple, they're more, the motion problems lean more towards an object rolling off a table or an object projected horizontally. That's where that's the focus, because that's the focus I found of the AP. So
Okay, thank you.
you're welcome. Okay. What else is there?
Can you do 15 on the Test Wizard?
Sure. Which one is it? 1 or 2? Is it Test Wizard? Was that 1 or is it 1?
It says homework 1, yeah.
Yeah, okay. 15. Okay. What is it? Okay, good question. Because you're going to have a dragging box problem. This is a challenging one. I think it's even more challenging than the one you have, but you'll follow the exact same procedure. What do you know? You know the force right away. And this is one of those things we unfortunately have to answer in terms of the variable. I know you're not happy about that. Look at what I did here is what you should do. I'm told that these two boxes are M, so I put it right into the picture. I don't know the first box. Also know that the this little tension over here is 1/2 F, and this tension over here is F. So I just look, it's F, it's M, it's A. Here's another question. How do you do it? Well, this is a second law problem. Anything involving F, M, and A, Newton really, he just, he, in his second law, everything about F and this is the beginning and the end. This is the only approach you'd use. So what do I do? So I said, okay, what do I know? I have to find the mass. But let's just go with Newton because F equals ma. The F, what is it accelerating? All objects, the M, and the unknown one. Am I doing it right when I'm doing 4? This is the right one I'm doing for 14? Am I doing the right?
both?
Oh yeah, okay. So all right, so let me do Newton's second law. I did this, and F equals m plus x, I don't know, times the acceleration, and I don't know that either. Then I do, what else can I work with? I've got 1/2 F equals m plus m. You know, look at this over here. And I go, what did I do that over here? Okay, I'm going to do it over here. I don't know where I did it, so I'll just do it here. 1/2 F, I'm told, accelerates what? Well, 2m times a. And you know what I realized? That F equals 4ma. That's terrific. Because now I have two equations. I have F equals 4ma. And I get, see what I did over here? Yeah, here's what I did. I did it down here. So F equals 4ma. And so I bring it up here. F equals m plus x times a. But F also equals 4ma. And so I set these two equal to each other. Why? Because now I can find x in terms of what they want me to do in terms of m. So you see that the a's cancel out. See what I did? Right over here, I canceled out the a's on both sides. 2m plus x is 4m. Here's right. Let me clean this mess up here a little bit. Okay. And so cross out the a's. 2m plus x is 4m. Well, subtract 2m from both sides. And I got my answer. So I'll just recoup what I did. I put all of my information into the picture because they talked about F, M. You know, there's only one equation that's going to help me with F and M. That's F equals ma. And I have two F's, so why not do F equals ma for both? So I did that here, did it for the first one. And then I did it again. Why not? And then I see that I've solved for F. And since F equals 4ma and F also equals m plus x, set them equal to each other, cross out the a's, and do some algebra. And I see that x equals 2m. So I'll do the next one. What is the tension connecting the B and C? So that's the last little. So I do another equation with B and C. So, well, that F that I don't know, I'll call it F underscore from B to C equals ma. And then what did I do? I went over here and I say that what is, if F equals 4ma, right? Equals 4ma, and I could solve for 4ma. What I could do is I could replace, because remember, I'm not satisfied with F equals ma because they want me to do in terms of F. So why don't I just take this equation I have and say A equals F over 4m and bring it in here. And that's what, and I substitute my A with F over 4m, and my m's cancel out, and I get the answer. So that's quite, I think my question on the test is easier than this, but it's good to be challenged because when the test comes, it'll be a lot easier for you. And how about we'll
Mr. Mangiacapri?
Yeah.
There was a question that you had said in class. It was a multiple choice question, and you were like, oh, this will be on the midterm. Don't get tricked. It was like, which one wouldn't change? And I think you had said it was about like position or momentum.
Um,
Do you remember?
which- does anybody remember which one wouldn't change? Don't get tricked. Like vaguely remember saying, oh, yeah, I got it. Okay. Which, if his body is moving, it's so simple. It's sometimes a question so simple you could be fooled, and I get that sense that you could be ready. What must be true about a moving object? It must change speed? No, a moving object doesn't have to change speed. Must change acceleration? No, it doesn't have to change acceleration. It must change position. I mean, you can't refute that. And if an
Okay,
object
thank
is
you.
moving, remember that was the one. Yeah. Gotta be, that's just you can't refute that. It's got to change position. Doesn't have to get faster. It doesn't have to change direction.
Could you
gotta-
repeat that, please?
Say that again. What?
Could you repeat like the options, please?
Okay, what's true about a moving object? It has to change direction? No. Moving object doesn't have to change direction. Has to change speed? No, it doesn't have to change speed. It could still be moving. It has to change acceleration? No, it doesn't have to change acceleration. It has to change position. Yeah, it's got to. You're not moving it if you're not changing position. It's just period, end of sentence. So be careful with that one. Go ahead. Who's that, Tori? What should we do, Tori? Tori, I don't think you have your speaker on. Or maybe do I have to choose you or something like that? Maybe I have to pick you or something. Or did you accidentally raise your hand, Tori? Tori, I think your volume's not on if you're speaking. Sorry, my mic is working. Do you want to type it in? Let me see. How do I get the? Oh, here it is. I can get this way. Sorry. Did you have a question, Tori, before we close up? Anybody have a? Yeah, there are. How about this one over here? I'll come up with something that'll help you. Okay. You got this tape. I've showed it to you before, but get a table. It's got a pulley here. Got some weights. Maybe the little weights over here. What are the questions? What would the free body diagram be for these weights? Let me see. No, let me ask you a different. So you got to. Let me just go over what I gave you before. So now, suppose this string is cut, and you got a box here. What happens to the acceleration of the system? Does the acceleration go up, down, or does it stay the same? So who knows? So you're placing a box, and you put a little hook over there, and you hook over there. Now the system, let's say the system still accelerates this way, and this is frictionless. So tell me, girls, who knows? Is the acceleration? Oh, getcha. How do I do this? How do I call on you? Is this hands raised? We'll go with Tori's. Yeah, your sound's not working. Kara, what happens to the system?
The acceleration decreases,
Of course, because tell them why.
the mass increases.
Yeah, the net force doesn't change. Do you get that? Because this people don't realize. Some people this exerts no net force. It's just on a frictionless table. The acceleration depends on two things: net force, which doesn't change, but the mass increases, so the acceleration decreases, right? So you would say the acceleration of the system decreases, right? Because you'd show the equation that acceleration and mass have an inverse relationship.
How do you know that the mass increased?
Well, look, my system now has three objects in it. You got M1, M2. What I was saying is before the mass was placed on the table, we had a string and two masses, right? And why did it accelerate? Because this is a bigger box, and it would be what mg. In fact, what if you ask the equation to be big mg minus little mg? What are they accelerating before that box? That would be the acceleration, right? But now, what's the deal now? Well, the net force doesn't change, right? Still this. But what do you got here? M plus this new box. You see that? This black box right there. Well, now you have more mass on the bottom, don't you? So the acceleration will go down because the mass went up. Does that explain things for you?
Yes, thank
Yeah,
you.
yeah. See, the net force doesn't change, and that's a frictionless table. You put friction in there, then you got to do a whole lot more thinking about that one. But let's say the table's frictionless. Let's take one more question, then we'll call it a night.
Could you just do the free body diagrams for those?
Yeah. Let's do the free body diagram before let's just take away this box. You're out of the picture. So each box has a tension. Now, if this is remember one string, one tension, it's a tension here and a weight. And let's make these boxes, the correct sizes. So we'll have a little box and a big box. So the tension, these tensions would be equal, wouldn't they? And this weight would be bigger, wouldn't it? Now, I don't make actually this tension would be bigger because the acceleration is in this direction. So I have to make this littler if you're showing relative sizes. So this is something I showed you in class, in both classes, okay? Sorry for being so sloppy, but this will have a big force, right? This because the acceleration is this direction, this down force should be bigger than the up force. Since this is accelerating this way, this up force should be bigger. And these two would be equal, wouldn't they? Okay.
For number 20 on the tip sheet, it was kind of similar to the pulley thing, but instead of like being on a table, it was a pulley on like a ramp where it looked like a triangle, and then the big M was on the ramp and the little M was hanging on the other side. The tensions would still be equal, right?
If it's one string, it's one tension over a massless pulley, and all our pulleys are massless. I don't know what sheet are we referring to?
The tip sheet, number 20.
Oh, the tip sheet. Okay. This here, right?
Yeah.
Oh yeah, one string, one tension. Yeah. So this is a single tension. This is T, and that's T. Yeah. It's just that the let's say it's at rest. So this up equals this down, and this right equals this left. It says it's at rest, and that's it, girls. All right.
Mr. Mangiapari.
Yeah.
Is everything on our reference table? Like we don't have to memorize anything, right?
Everything's on the reference table. Yeah.
Okay, and A and G are 10 for the midterm,
10,
not 9.8.
not 9.8.
Okay.
Plus, if you use 9.8, nobody's gonna mark you wrong. But you can use 10. It's a lot easier. All right.
Okay.
Do we need
Okay.
a protractor?
What's that?
Do we need a protractor?
Yeah, you need pen, pencil, protractor, ruler, calculator.
Are we gonna have to like draw angles, or is it just to like make lines straight?
Make lines straight. Angles, I don't remember asking you to do any angles, but you could do angles, can't you? You could draw angles with a protractor. Right?
Are there questions that are like words as the answer?
Yeah, you could be asked to explain things, yeah.
So do we need both a protractor and a ruler, or is just like
Well, if your protractor has a ruler, you're fine.
Okay, thank you.
Yeah.
For drawing like the relative sizes, do we have to measure exactly like if they're the same? Do we have to measure like 1 inch, or no? We can just
Just
eyeball it.
make them identical.
Okay, just eyeball it.
If you have forces that are equal, make them identical.
Okay, so you don't have to like draw them exactly, like just eyeball it.
Yeah.
Okay.
Okay, girls, good luck. Ready? And I'll post this video, okay? Bye.
Thank you.
Thank you.
Thank
Welcome.
you.
Thank you.
Thank you.
Yeah.